So, why can an astronaut fall into a black hole in minutes, while a distant camera never records the instant they cross the event horizon? The unsettling claim is that even with perfect optics, the astronaut's image just dims, reddens, and seems to freeze outside the edge. A black hole is a region where gravity is so strong that, past a certain boundary, no light signal can escape to faraway space. That boundary is the event horizon, and it is defined by what light can do, not by what your nerves can feel. Now imagine two observers, the falling astronaut with a wristwatch and a second astronaut far away with a clock and a live video feed. How can one story include a crossing in finite time, while the other story never reaches the crossing frame at all? An event horizon is not a solid surface, and you do not smash into it. In general relativity, space and time form spacetime, and gravity is curvature in that geometry. Light follows the straightest possible routes, and the event horizon is where even outward-directed light routes are bent back inward. That makes the horizon a one-way boundary for information. Once you're inside, no future flashlight beam or radio ping can reach a distant spacecraft. Another surprise follows. Tidal forces, the stretching from gravity changing with distance, can be small at the horizon of a supermassive black hole because the horizon sits far from the central mass. So if crossing is not marked by a jolt, the missing video frame must come from how signals behave near the boundary. What does gravity do to time itself as you approach that boundary? Gravitational time dilation means a clock deeper in a gravitational field accumulates less proper time, the time measured by that clock itself, than a clock far away, because space-time curvature changes the rate at which time flows. This is experimentally confirmed. GPS satellites and ground receivers must correct for it, and atomic clocks tick measurably differently on a mountain than at sea level. Picture the falling astronaut sending a sharp radio beep every second, according to their wristwatch. A distant receiver gets those beeps farther and farther apart, and each beep shifts to a lower frequency, a change called gravitational redshift, because climbing out of the gravitational field reduces the signal's energy. To the distant camera, the astronaut's motion is paced by those stretched-out signals, so the approach to the horizon looks slower and slower, pushing the crossing out of reach. The last light from the astronaut is not merely late, it is stretched toward invisibility. The astronaut measures proper time, the wristwatch time, and in that time the horizon is reached after a finite number of ticks. The distant observer uses a faraway clock and the arrival of light, and general relativity predicts those arrivals take longer and longer as a mission happens closer to the horizon. A helmet lamp would shift from white to red to infrared to radio, while the gaps between photons widen. Each photon also arrives with less energy, so the image fades into the background glow of space, including the cosmic microwave background, leftover radiation from the hot early universe. So the camera never records the crossing because the information is redshifted and delayed beyond usable limits. If the outside world never gets a clean crossing signal, how does a black hole gain mass or merge with another black hole in a way we can measure? Seeing is about photons, but gravity is the structure of space-time, and changes in that structure spread outward at the speed of light. Astronomers track stars orbiting Sagittarius A, the compact object at the Milky Way's center, and infer about 4 million suns of mass without ever filming a horizon crossing. When matter falls in and its light becomes too redshifted to detect, the external gravitational field still reflects that added energy, so distant orbits behave as if the black hole is heavier. In mergers recorded by LIGO and Virgo, laser interferometers that detect gravitational waves, ripples in space-time, the chirp ends in a fading ringdown that matches a newly formed larger black hole settling down. And here is the deeper twist. An event horizon is defined by which light rays ultimately escape to infinity, so its exact location depends on the whole future space-time, not on a local marker you can film. The contradiction comes from treating time as universal, like one master clock for everyone. Relativity gives each observer proper time, while the distant camera builds its story from the arrival times of light and radio signals. The falling astronaut crosses the horizon after finite wristwatch time because free fall is local, and nothing special has to happen at that boundary for a large black hole. But the distant observer never receives any light emitted from inside, and the last light from just outside is delayed and redshifted without bound, so the video never contains a final crossing frame. That resolves the opening question. The crossing is real for the astronaut, yet unobservable from far away because the photons that would announce it cannot escape. Once you see the horizon as a causal boundary, what can influence what, the paradox disappears. Like if this was interesting, hit the subscribe for more and turn that notification bell on